The research vessel had been anchored in the same position for 3 hours, its multi-beam sonar sending pulses of sound downward into the water and recording what came back. When the image on the monitor changed in a way that stopped the conversation in the survey room, the scientists who had been talking about calibration parameters and water column corrections in the coffee that had gone cold in someone's cup all looked at the screen at the same time. The image showed the seafloor in cross-section, a jagged and complex terrain of ridges and basins and sediment layers laid down over millions of years. They had been mapping this section of the Makassar Strait, the body of water that separates the Indonesian island of Sulawesi from the island of Borneo, for 11 days. They had covered hundreds of kilometers of seafloor with a sonar, and had found the kinds of features they expected to find in a region of complex and active tectonics. And then, in a section of seafloor that the existing geological maps had described as relatively undifferentiated basins, the sonar showed something else. The feature ran across the monitor screen from left to right, a linear discontinuity in the sediment layers that could not be explained by any depositional or erosional process that the lead scientist, who had been studying Indonesian tectonics for 16 years, had encountered in this region. The sediment layers were offset. On one side of the feature, the layers sat at one elevation. On the other side, they sat at a different elevation, and the difference was not gradual or transitional in the way that slow compaction or differential settling would produce. It was abrupt, the kind of abruptness that has only one geological explanation. Something beneath the seafloor had moved. Something had displaced the rock and the sediment above it, and the displacement had been large enough and sudden enough to produce the sharp, vertical discontinuity that was now showing on the monitor in a research vessel anchored in waters that the scientific community had not previously identified as a location of active surface faulting. The lead scientist took a photograph of the screen with her phone. She sent it, with a brief message, to 3 colleagues at universities in Indonesia, Australia, and the Netherlands who had been working on the regional tectonic picture of the Sulawesi region for years. The message read, "We need to talk about this." The photographs were followed, over the next several weeks, by the full processed sonar data, by the gravity and magnetic data that the vessel had been collecting simultaneously with the sonar survey, and by a series of video calls that grew progressively longer and more detailed as the implications of what the data was showing became clearer. By the time the research team submitted their findings for peer review, 6 months after the discovery in the Makassar Strait, the fracture they had found had been extended in the geological analysis from the initial section of sea, where it was first observed, to a structure that ran for more than 200 kilometers through the subsurface beneath one of the most seismically complex and densely populated island environments in the world. And the implications of what they had found for the communities along the shores of Sulawesi, and for the broader question of how well the scientific community understands the tsunami hazard in the Indonesian archipelago, were alarming enough that the peer review process for the paper was accompanied by a parallel conversation with emergency management agencies about what the findings meant for current risk assessments. This is the story of what they found, and what it means. Sulawesi is an island of extraordinary geological complexity. Its shape alone, a four-armed form, unlike any other major island in the world, is a product of the tectonic collision and amalgamation of multiple distinct crustal fragments over tens of millions of years. Fragments that originated in different places and that were assembled into their current configuration by the relentless movement of the plates that surround the Indonesian archipelago. Understanding Sulawesi's geology requires understanding that the island is not a coherent geological unit in the way that, for example, a continental craton is coherent. It is a collage, a patchwork of terrains with different rock types, different histories, and different mechanical properties, all of which have been compressed and rotated and thrust against each other by the extraordinary tectonic complexity of the region. That complexity arises from the fact that Sulawesi sits at the intersection of 3 of the world's major tectonic plates. To the west and south, the Eurasian plate and the Indo-Australian plate are converging, driving the subduction that feeds the volcanic arcs of Sumatra and Java, and the older subduction systems that have built the geological foundations of much of the Indonesian archipelago. To the east, the Pacific plate is also converging toward the region, its motion complicated by the presence of the Philippine Sea plate and a collection of microplates and oceanic terrains that make the eastern Indonesian tectonic environment one of the most complicated on Earth. Sulawesi sits in the middle of this intersection, and its geology reflects the fact that it has been pushed and pulled and rotated by forces, arriving simultaneously from multiple directions over geological time. The practical consequence of this tectonic complexity is that Sulawesi has faults everywhere, not a few large well-understood faults, and a background of smaller structures, but an intricate network of active and potentially active fault systems that cut through the island's crust in multiple orientations, that interact with each other in ways that are not always predictable from the individual characteristics of each fault in isolation. And that seabed, over the historical and geological record, produced earthquakes and tsunamis that have caused significant casualties and destruction. The Palukoro Fault, which runs north-south through the central arm of Sulawesi and through the city of Palu, is one of the fastest slipping strike-slip faults in the world, moving at rates of several centimeters per year. In September 2018, the Palukoro Fault produced a magnitude 7.5 earthquake that triggered a localized but devastating tsunami in Palu Bay and caused a phenomenon called liquefaction, in which the saturated sediments of the Palu Valley essentially turned to liquid under the seismic shaking, engulfing entire neighborhoods in a flow of liquefied soil. More than 4,000 people died. The event forced a painful reassessment of the tsunami hazard in confined bays along the coast of Sulawesi, where the geometry of the coastline can focus tsunami energy in ways that produce wave heights far beyond what would be generated on an open coast by the same earthquake. The fracture that the research vessel found in the Makassar Strait is a different kind of structure from the Palukoro Fault. It is not a strike-slip fault, where the two sides slide horizontally past each other. The geometric character of the offset that the sonar imaging revealed, combined with the gravity anomaly data that showed a density contrast consistent with vertical displacement of deep crustal material, and combined with the seismicity analysis that the research team conducted using the regional earthquake catalog, is most consistent with a thrust fault. A thrust fault, as distinct from a strike-slip fault, is one in which compressional stress causes one block of crust to be pushed up and over another. Thrust faults are particularly significant for tsunami generation, because the vertical component of fault slip displaces the seafloor upward, and when the seafloor moves upward, it displaces the water column above it, producing the initial perturbation that propagates outward as a tsunami wave. The significance of finding a previously unknown thrust fault of the size and character that the research team has identified in the Makassar Strait cannot be overstated in the context of Indonesian tsunami hazard. Indonesia's official tsunami hazard maps, which are used by coastal planners, by the National Disaster Management Agency, and by the warning systems that are supposed to give coastal populations time to evacuate when an earthquake occurs, are based on a model of the fault systems that can generate tsunamis. If they have fault systems capable of generating tsunamis that are not in that model, the hazard maps are wrong. The warning systems may not respond appropriately to an earthquake on an unmapped fault. The evacuation routes may not be designed for the correct inundation scenario. The buildings in coastal areas may have been sited on the assumption of a tsunami hazard that is smaller than what an unmapped fault could produce. Every gap in the fault map is a gap in the hazard assessment, and the fracture in the Makassar Strait is a significant gap. To understand why a thrust fault in the Makassar Strait would generate a tsunami that could affect Sulawesi's western coast, and why the characteristics of that coast make the potential tsunami particularly dangerous, it is necessary to understand a little of the physics of tsunami generation and propagation. A tsunami is not simply a very large wave of the kind that surfers chase and coastal engineers design seawalls for. It is a different category of ocean wave, one that is distinguished from ordinary wind-driven waves by its wavelength, the horizontal distance between successive wave crests, and by the relationship between its wavelength and the depth of the ocean it is traveling through. Ordinary ocean waves have wavelengths of meters, 200s of meters. Tsunamis have wavelengths of hundreds of kilometers. This difference in wavelength has profound consequences for how the wave behaves. A wave whose wavelength is very much larger than the ocean depth it is traveling through behaves as what oceans call a shallow water wave, regardless of the actual depth of the ocean. The Pacific Ocean might be 4 kilometers deep, but a tsunami wavelength of 300 kilometers is so much larger than that depth that the wave feels. The bottom of the ocean and its behavior is governed by the depth. For a shallow water wave, the wave speed is proportional to the square root of the water depth. In the deep open ocean, where the depth is several kilometers, this gives tsunami wave speeds of several hundred kilometers per hour, faster than a commercial aircraft at cruising altitude. As a tsunami approaches shallower water near the coast, it slows down, but slowing down does not cause the tsunami to lose energy. The energy is conserved, and as the wave slows and compresses in the shallower water, its height increases. The wave that was perhaps a meter or two high in the deep ocean, easily overlooked by a ship on the surface, steepens and rises as it approaches the shore, arriving as the terrifying wall of water that coastal communities near the source of a major submarine earthquake sometimes have only minutes to flee. The geometry of the Makassar Strait introduces a specific concern for the potential tsunami hazard from the newly discovered fracture. The strait is approximately 250 kilometers wide at its broadest and narrows significantly toward its northern and southern ends. The western coast of Sulawesi, that borders the strait, which includes the city of Makassar, the largest city in eastern Indonesia, with a population of approximately 2 million people, and numerous smaller coastal communities stretching both north and south, is a relatively low-lying coast in many areas. The coastal plain west of Makassar, where the city's port facilities and much of its residential and commercial development is concentrated, sits only a few meters above sea level over large areas. The combination of the low coastal topography, the presence of large urban populations close to the waterline, and the relatively confined geometry of the Makassar Strait, which could focus tsunami energy rather than allowing it to spread in all directions over open ocean, creates a scenario that the research team's preliminary tsunami modeling has characterized as potentially producing run-up heights in coastal areas that would be far greater than anything the current hazard maps project for this part of Sulawesi's coast. The specific run-up projections that the team's tsunami models produce depend on assumptions about the fault's geometry, its potential slip amount, and the degree to which different segments of the fault might rupture simultaneously or in sequence. These parameters are not known with precision from the current data. The sonar imaging gives a surface trace of the fracture and the geometry of the sediment offset, but it does not directly measure the fault's dip angle at depth, the length of the fault surface that is locked and accumulating stress, or the recurrence interval of large ruptures. The gravity data provides some additional constraint on the fault's deeper structure, but the resolution of gravity measurements in a marine environment is limited, and the models derived from the gravity data carry significant uncertainty. The team's tsunami modeling has therefore been conducted across a range of fault parameters, producing a range of tsunami scenarios from moderate to severe, and it is a severe end of that range. The scenarios that involve rupture of a larger portion of the fault system, that the emergency management agencies who have been briefed on the findings have found most concerning. The discovery of the fracture is set against a broader backdrop of what Indonesian scientists and the international geophysical community have been learning about the nature of tsunami hazard in the archipelago since the 2004 Indian Ocean tsunami and the 2018 Palu event. Both of those disasters forced revisions to the scientific understanding of how and where tsunamis could be generated in Indonesian waters, and both demonstrated that the actual tsunami hazard was larger and more geographically complex than the models in use at the time had suggested. The 2004 Indian Ocean tsunami, generated by the magnitude 9.1 Sumatra Andaman earthquake, is the most deadly tsunami in recorded history, killing approximately 230,000 people across 14 countries. The earthquake that generated it was not entirely a surprise, since the Sunda Megathreus subduction zone that produced it was known and had been identified as capable of major earthquakes. What was not adequately anticipated was the magnitude of the event, the degree to which the fault ruptured across multiple segments simultaneously, and the resulting height of the tsunami in the regions closest to the source. The hazard models that were in use in 2004 underestimated the size of the earthquake that the Sunda Megathreus was capable of generating, and that underestimation translated directly into inadequate tsunami warning infrastructure, inadequate evacuation planning, and a death toll that, with better science and better preparation, would have been substantially lower. The 2018 Palu tsunami was a different kind of surprise. It was generated not by the thrust motion that produces the largest tsunamis on offshore subduction zones, but by the strike-slip motion of the Palu Coral Fault as it passed beneath Palu Bay. Strike-slip earthquakes were not considered in the hazard models that were in use in 2018 to be efficient generators of local tsunamis. The assumption was that the horizontal sliding of strike-slip faults produced little vertical seafloor displacement, and therefore little tsunami generation potential. What the Palu event demonstrated was that this assumption was wrong in certain geometric configurations, specifically in situations where a strike-slip fault runs through a confined bay, and where the fault's movement can produce vertical displacement through the mechanism of coupled horizontal and vertical motion at bends in the fault trace. The tsunami that arrived in Palu Bay within seconds of the earthquake, before the official tsunami warning had been issued, before most coastal residents had any indication that a wave was coming, killed thousands of people in a few minutes. The lessons drawn from both of these events, and from the smaller but still significant tsunami events that have occurred in Indonesian waters in the years between and since, have driven sustained investment in the improvement of Indonesia's tsunami hazard understanding. New submarine surveys have been conducted. New seismic reflection data has been collected. New paleoseismic investigations have been carried out in coastal areas where the geological record might preserve evidence of past tsunamis. New numerical modeling has been applied to refine the tsunami scenarios associated with known fault systems. The effort has been substantial, and the improvements to the hazard picture have been real. But the discovery of the fracture in the Makassar Strait is a reminder that the improvements, however significant, are incomplete. There are still major structural features in Indonesian waters that have not been mapped. There are still faults capable of generating tsunamis that are not included in the official hazard assessments. The work of understanding the Indonesian seismic and tsunami hazard is not finished, and the most consequential of the remaining unknowns may be the ones that are still completely unknown, because no one has yet looked in the right place with the right instruments. The research team's investigation of the fracture did not stop with the sonar data and the gravity measurements collected during the initial survey. In the months following the discovery, the team undertook a systematic reanalysis of the existing seismological data for the Makassar Strait region, examining the historical earthquake catalog for evidence of past seismic activity that might be associated with the newly identified fault. This kind of retrospective seismological analysis is a standard component of fault characterization studies, and it can provide valuable information about the activity level of a fault, even when the fault has not produced a historically recorded major earthquake. The results of the seismological reanalysis were sobering. When the team applied the location of the fracture to the catalog of earthquakes that had been recorded in the Makassar Strait region over the past several decades, a pattern emerged that had not been visible when the seismological data was examined in isolation. Several clusters of moderate seismicity, earthquakes in the magnitude 4 to 5 range that had been recorded by the Indonesian National Seismograph Network, but that had not been associated with any specific fault structure in previous analysis, aligned spatially with the fracture trace identified in the sonar data. The alignment was not perfect, because earthquake location uncertainties in an offshore region with sparse seismic network coverage can be tens of kilometers. But it was suggestive of a fault system that had been producing seismic activity and that had simply not been identified as a coherent structure because the data needed to connect the individual earthquakes to a common fault had not previously been available. The magnitudes of the earthquakes in the catalog that appeared to be associated with the fracture were modest. The largest was a magnitude 5.1 event that had occurred in 2019 and that had been noted in the national catalog but had not attracted significant scientific attention because there was no known fault in the area to connect it to. Moderate earthquakes in the magnitude 4 to 5 range do not, on their own, pose a significant tsunami hazard. The concern is not that the fracture has been generating small earthquakes that have gone unnoticed. The concern is that a fault system that has been generating small earthquakes is a fault system that is actively accumulating stress, and a fault system that is actively accumulating stress is a fault system that is capable of eventually releasing that stress in a much larger event. The small earthquakes are not a sign that the hazard is manageable. They are a sign that the fault is alive, that it is part of the active stress field of the region, and that it merits the same kind of careful monitoring and hazard assessment that is applied to known active faults. The most critical parameter for assessing the tsunami generation potential of the fracture, and the one that the current dataset is least able to constrain, is the fault's potential maximum earthquake magnitude. This parameter depends on the fault's total rupture area, which is the product of its length and its width, the amount of slip that occurs during a major rupture, and the mechanical properties of the fault zone material. The fault length is the parameter that is best constrained by the current data, since the sonar imaging has traced the surface expression of the fracture over approximately 200 kilometers. The fault width, which depends on how deep the fault extends into the crust, and on the dip angle at which it descends, is much less well constrained. The team's current estimates of fault width, based on the geometry of the sediment offset, and on comparisons with analogous thrust fault systems in similar tectonic environments, span a range from approximately 30 to 70 kilometers. The uncertainty in this single parameter translates, through the standard scaling relationships between fault area and earthquake magnitude, into a range of possible maximum earthquake magnitudes from approximately 5 to 8.2. The difference between a magnitude 7.5 and a magnitude 8 to earthquake may not sound dramatic in casual conversation. In terms of the tsunami they would generate in the Makassar Strait, the difference is enormous. A magnitude 7.5 thrust earthquake on the fracture, with its source relatively close to the western coast of Sulawesi, would generate a tsunami that the team's models suggest could produce run-up heights of several meters in the most exposed coastal areas. This would be damaging and potentially fatal in low-lying communities that had not received warning. A magnitude 8 to earthquake on the same fault, with several times more fault area rupturing and several times more total slip, would generate a tsunami whose run-up heights in the same coastal areas could reach tens of meters. The difference between those two scenarios is the difference between a serious disaster and a potentially catastrophic one. The tsunami that the fracture could generate would, if it occurred without warning, follow a timeline that is determined by the physics of wave propagation in the Makassar Strait. From a rupture on the newly identified fault, the first tsunami waves would reach the nearest sections of the western Sulawesi coast in approximately 10 to 20 minutes, depending on the exact source location and the coastal geometry. 10 to 20 minutes is the same brutal time constraint that confronted the residents of Palu Bay in 2018 is less time than it takes to drive from a beach to high ground in a congested coastal city. It is less time than many warning systems, even well-functioning ones, require to detect an earthquake, assess its tsunami generation potential, and issue a warning that reaches the population at risk. The inadequacy of this time constraint for conventional earthquake-based tsunami warning is one of the most challenging aspects of the local tsunami problem in Indonesia and in other regions where tsunami-genic faults sit close to populated coastlines. The standard model of tsunami warning, which was developed primarily in the context of distant tsunamis, where the wave travel time between the source and the target coast is measured in hours rather than minutes, has substantial lead time available for detection and warning issuance. The 2004 Indian Ocean tsunami, which devastated coastlines across the Indian Ocean basin, was the event that motivated the development of the Indian Ocean Tsunami Warning and Mitigation System, which now provides warning capabilities for tsunamis generated in the Indian Ocean. For tsunamis generated in distant subduction zones, this system can provide tens of minutes to hours of warning time, enough for coastal communities to evacuate. For tsunamis generated by faults within the Makassar Strait, the warning time problem is fundamentally different. By the time an earthquake occurs, is recorded by the seismic network, is analyzed by the automated algorithms that screened for tsunamis, and a warning is issued through the official channels to the coastal communities at risk. The tsunami may already be approaching the shore. The Indonesian Meteorology, Climatology, and Geophysical Agency, known by its Indonesian acronym BMKG, operates the National Tsunami Warning System, and the system has been substantially improved since 2004. But even the most efficient warning system cannot overcome the physics of a fault that is close to the coast and a wave that travels at several hundred kilometers per hour in the shallow water of the strait. The solution that the scientific and emergency management communities have developed for this class of problem, the locally generated tsunami, where the wave arrival time is too short for conventional warning, is the concept of natural warnings. The idea is to educate coastal populations to treat the earthquake itself as the warning, to recognize that strong and prolonged shaking near the coast is itself a signal that a tsunami may be coming, and that the appropriate response is immediate self-evacuation to high ground without waiting for an official warning. Tisaprach, which has been incorporated into public education programs in Indonesia and in other tsunami-prone, has the advantage of being insensitive to the performance of the warning system infrastructure. If a person knows that strong ground shaking means run to high ground, they will run regardless of whether the official warning arrives in time or not. The challenge is that the natural warning approach works best when the population at risk is aware of it, when they have been educated about the specific threat, and when the evacuation routes and destination points are well understood and accessible. In the case of the newly discovered fracture in the Makassar Strait, the population along the western coast of Sulawesi has not previously been educated about the specific tsunami hazard from a fault in this location, because the fault was not known to exist until the research vessel found it. The hazard maps that would have informed any evacuation planning, any building siting decisions, any land use policies for the coastal zone did not include this fault. The communities that live closest to the fracture, and that would therefore have the least warning time if the fault ruptured, are communities that may not have made the infrastructure and planning investments appropriate to the level of tsunami hazard that the fracture represents. The city of Makassar presents a specific and complex challenge in the context of the new findings, with a population of approximately 2 million people and a waterfront that sits at the interface between the urban fabric of one of Indonesia's largest cities and the Makassar Strait. It is by any measure a significant concentration of people and infrastructure at potential risk from the tsunami hazard associated with the newly discovered fault. The city's port facilities, which handle a substantial portion of the cargo traffic for the eastern Indonesian archipelago, sit at the waterfront. The fishing industry that supports a significant portion of the coastal population's livelihoods is based at the waterfront. The informal settlements that are a feature of Indonesian coastal cities and that house populations that are particularly vulnerable in disaster scenarios because they have limited resources for preparation and limited political influence in the allocation of disaster risk reduction investment, are concentrated in low-lying coastal areas. The question of what the discovery of the fracture means for Makassar is not one that has a simple answer. It does not mean that a tsunami is coming soon, in the same way that the discovery of any fault does not mean that an earthquake is imminent. Faults can remain inactive for centuries or millennia between major ruptures. The recurrence interval of large earthquakes on the newly discovered fracture is completely unknown from the current data because the paleoseismic investigation that would be needed to estimate the recurrence interval, trenching across the fault trace on land where the structure comes close enough to the surface to be accessible, or conducting deep-sea sediment coring in the basin areas adjacent to the fault where the sedimentary record of past tsunami deposits might be preserved, has not yet been carried out. The fracture could be a fault that last ruptured in a major earthquake hundreds of years ago, and that is still far from the end of its loading cycle. It could be a fault that last ruptured 1,000 years ago, and that is now approaching the end of its loading cycle. The current data does not allow those possibilities to be distinguished. What the discovery does mean for Makassar, and for the coastal communities of Western Sulawesi, is that the hazard assessment that their planning and preparedness has been based on is incomplete in a material way. The tsunami hazard from the newly discovered fracture is real. It is currently unquantified because the fault parameters needed to quantify it are not yet known with sufficient precision, and it is not currently incorporated into the official hazard maps that govern coastal land use planning, evacuation route design, and early warning system configuration for the region. Addressing this situation requires investment in the scientific work needed to characterize the fault more completely. Investment in the engineering and planning work needed to translate the improved hazard assessment into updated maps and guidance. An investment in the public education and community preparedness work needed to ensure that coastal populations understand the threat and know what to do when the earthquake comes. The broader lesson that the discovery of the fracture teaches is one that Indonesian scientists and their international collaborators have been learning in stages since the 2004 tsunami. The lesson is that the Indonesian archipelago, for all the scientific attention that has been focused on it over the past 2 decades, is still not fully mapped in terms of its active fault systems. The complexity of the tectonic environment, the vast extent of the archipelago, the large proportion of the fault systems that are located in the submarine environment where direct observation requires specialized research vessels and sophisticated instrumentation, and the sheer scale of the mapping task relative to the resources available to the scientific community, have meant that the progress in understanding the archipelago's seismic and tsunami hazard, while real and substantial, remains incomplete. The discovery of the fracture in the Makassar Strait is not an isolated finding that represents the last significant gap in the hazard picture. It is a data point in a pattern of ongoing discovery, a reminder that there are likely additional unmapped structures in Indonesian waters that could generate tsunamis affecting populated coastlines, and that the process of finding and characterizing those structures is a scientific and humanitarian priority that deserves sustained support. The resources required to complete a comprehensive submarine fault survey of the Indonesian archipelago are substantial. The archipelago spans an enormous area, comprising more than 17,000 islands and surrounded by submarine environments that range from shallow shelf seas to deep ocean trenches. A systematic survey using the kind of high-resolution, multi-beam, sonar, and geophysical instrumentation that the research vessel deployed in the Makassar Strait would require many years and many research vessel deployments to cover the full area that is relevant to tsunami hazard. The cost of such a program, if it were to be conducted to the standard required to identify structures of the kind that was found in the Makassar Strait, would run into hundreds of millions of dollars. This is a large number, but it needs to be set against the cost of the alternative. The 2004 Indian Ocean tsunami caused approximately $10 billion in economic damage in Indonesia alone. In addition to its catastrophic human toll, the 2018 Palu earthquake and tsunami caused economic losses estimated at several $100 million in a relatively small regional economy, and killed more than 4,000 people. The cost of a future tsunami, generated by an unmapped fault in a major coastal city whose hazard maps did not account for the threat, could easily exceed either of these figures. The investment in hazard mapping is not simply a scientific expense, it is a risk management investment, and the actuarial case for making it is compelling once the scale of the potential losses is properly accounted for. The research team that discovered the fracture has been working, in the months since the initial finding, on 2 parallel tracks. The first track is the scientific work of characterizing the fault as completely as possible with the data that is currently available. This involves refining the interpretation of the sonar and gravity data, incorporating the results of the seismological reanalysis into the structural model of the fault, conducting additional numerical modeling of the tsunami scenarios associated with different fault parameter assumptions, and preparing the full analysis for publication in the peer-reviewed literature. The second track is the engagement with Indonesian government agencies, with international organizations involved in tsunami hazard reduction, and with the emergency management community to communicate the findings and their implications to the people who need to act on them. The engagement with the emergency management community has raised questions that the scientific analysis alone cannot answer, and that point toward the deeper challenges of translating hazard science into practical preparedness improvements. The emergency managers who have been briefed on the findings want to know, understandably, what to do. They want to know whether evacuation routes in coastal areas near the fracture are adequate for the tsunami scenarios that the fault could generate. They want to know whether the existing tsunami warning system configuration would provide adequate warning for a rupture on the newly identified fault. They want to know what building performance standards are appropriate for structures in the coastal zone adjacent to the fault. And they want to know how to communicate the new information to coastal communities without creating panic or undermining confidence in the official hazard maps and preparedness guidance that those communities have been educated to follow. These are not questions that have simple answers, and the scientists who discovered the fracture are not in a position to provide all of them. The translation from a scientific finding about a newly identified fault to the specific actionable guidance that emergency managers and community planners need is a multi-step process that requires the involvement of engineers, planners, communicators, and community members, as well as scientists. It is a process that takes time, and the time it takes is time during which the coastal communities at risk are operating with incomplete information about their hazard. The tension between the urgency that a significant scientific finding creates and the deliberate pace at which the institutional processes of hazard assessment, standard revision, and emergency planning revision operate is a familiar feature of the relationship between science and policy in the disaster risk management field. It is a tension that has been present in every major revision to the tsunami hazard understanding in Indonesia, and in other regions where large seismic events have forced reassessment of existing assumptions. The scientific community identifies a gap in the hazard picture. The implications of the gap are alarming. The communication of those implications begins. The institutional response is initiated, and in the interval between the scientific finding and the completion of the institutional response, the communities at risk are in a liminal state, no longer operating under the assumption that their previous hazard understanding was complete, but not yet operating under the revised guidance that the new understanding demands. The seafloor beneath the Makassar Strait holds more information than the research team has yet been able to extract from it. The sonar and gravity data collected during the initial survey have defined the fracture surface expression with good resolution, and have provided a first estimate of its deeper structure. But they have not answered the questions that matter most for hazard assessment: the rate at which the fault is accumulating stress, the recurrence interval of major ruptures, the slip that would accompany a major earthquake, the precise geometry of the fault surface at the depths where the rupture would initiate. These are the parameters that determine the tsunami the fault could generate, and they are parameters that require additional data to constrain. The paleoseismic investigation is the highest priority among the additional scientific work that the team has identified as needed. The technique of looking for evidence of past earthquake-generated submarine mass movements in the sediment record of basins adjacent to the fault has been successfully applied in other submarine fault characterization studies. Turbidite deposits, the layers of sediment that are deposited when underwater slopes fail and generate sediment gravity flows, can be dated, and their triggering events inferred, providing a record of past large earthquakes on nearby faults that extends back thousands of years. If such deposits are present in the sediment cores from the Makassar Strait basin and can be associated with rupture of the newly discovered fault, they would provide the recurrence interval data that is currently completely unknown. The additional seismic reflection survey data that would improve the constraint on the fault's geometry at depth is another high-priority investigation. Modern seismic reflection techniques, using controlled acoustic sources and dense arrays of hydrophone receivers deployed from a research vessel, can produce images of the subsurface to depths of several kilometers with sufficient resolution to map the fault's geometry through the seismogenic zone where rupture initiation occurs. These data would significantly reduce the uncertainty in the fault width estimate, which is currently the largest source of uncertainty in the maximum earthquake magnitude estimate. These investigations require resources, vessel time, scientific personnel, and the logistical infrastructure to conduct marine geophysical surveys in a region of the Indonesian archipelago that is not adjacent to a major research port. The Indonesian government, through BMKG, and through the National Oceanographic Research Agency LIPI, has the institutional infrastructure to support this work, but the resource allocation decisions that would enable it to proceed on an accelerated timeline require prioritization at a level that competes with many other legitimate demands on the limited budget available for marine geoscience in Indonesia. The international scientific community has been engaged with the research team through the peer review process and through the informal networks of the tsunami hazard research community, and there are ongoing discussions about the possibility of collaborative international surveys that would bring additional resources to bear on the characterization problem. The fracture in the Makassar Strait is not a unique finding in the sense that it represents a category of geological structure that had not previously been encountered. Unmapped submarine thrust faults in tectonically active regions are not a novelty in the geological literature. The literature of post-disaster surveys following major tsunamis contains numerous examples of faults that were identified after the fact, after the earthquake had occurred and the tsunami had arrived, when the urgency of understanding what had happened drove rapid mobilization of survey resources that would not have been available for pre-event characterization. The 2018 Palu tsunami, the 2004 Indian Ocean tsunami, and numerous smaller events around the Ring of Fire have each been followed by submarine surveys that found structural features that the pre-existing geological maps had not included. What makes the Makassar Strait discovery significant is not its novelty but its timing. It is a pre-event discovery. The research team found a fracture during a survey that was motivated by the general goal of improving the understanding of the tectonic structure of the Makassar Strait region, not by the need to understand a tsunami that had already happened. The scientific work was proactive rather than reactive. This is exactly the kind of work that the scientific and policy community has identified as the most valuable approach to tsunami hazard reduction, finding the hazardous structures before they produce the disaster rather than characterizing them afterward. The discovery in the Makassar Strait demonstrates that this proactive approach is feasible and productive. It also demonstrates that there is more to find, that the investment in pre-event submarine geological surveys in Indonesia and in other regions of high tsunami risk has returns that justify the cost many times over. The lead scientist, who was on the research vessel when the image changed on the monitor, who sent the photograph and the brief message to her colleagues, who spent the following months working through the implications of what the sonar had found, describes her current state of mind as a combination of scientific fascination and genuine concern. The scientific fascination is straightforward. She has found something important, something that advances the understanding of a region she has studied for 16 years, and that contributes to the broader goal of characterizing the tsunami hazard in Indonesia with the completeness and accuracy that the hazard demands. The concern is equally straightforward. She knows what a tsunami can do to a coastal city. She has been to Palu. She has seen the photographs from 2004. She knows that the fracture she found is real, that it is active, that it is capable of generating a tsunami, and that the communities along the coast that would be affected by that tsunami are currently not aware that the threat exists at their doorstep. This combination of scientific fascination and genuine concern is appropriate to the situation. The fracture is there. The science is describing it. The question is, what happens next? The research vessel that found the fracture has returned to port. The data from its survey is being analyzed. The paper describing the findings is moving through the scientific literature. The conversations with emergency management agencies are ongoing. The coastal communities along the western shore of Sulawesi are going about their lives, living and working in the proximity of a hazard that they do not yet know exists. The seafloor beneath the Makassar Strait holds its fracture in silence, accumulating stress at the rate that the tectonic forces of the region impose on it, as it has been accumulating stress since the last time it moved. When it will move again is not known. That it will move again is not in doubt. The research vessel had been anchored in the same position for 3 hours, its multi-beam sonar sending pulses of sound downward into the water and recording what came back. When the image on the monitor changed in a way that stopped the conversation in the survey room, the scientists who had been talking about calibration parameters and water column corrections in the coffee that had gone cold in someone's cup all looked at the screen at the same time. The image showed the seafloor in cross-section, a jagged and complex terrain of ridges and basins and sediment layers laid down over millions of years. They had been mapping this section of the Makassar Strait, the body of water that separates the Indonesian island of Sulawesi from the island of Borneo, for 11 days. They had covered hundreds of kilometers of seafloor with a sonar, and had found the kinds of features they expected to find in a region of complex and active tectonics. And then, in a section of seafloor that the existing geological maps had described as relatively undifferentiated basins, the sonar showed something else. The feature ran across the monitor screen from left to right, a linear discontinuity in the sediment layers that could not be explained by any depositional or erosional process that the lead scientist, who had been studying Indonesian tectonics for 16 years, had encountered in this region. The sediment layers were offset. On one side of the feature, the layers sat at one elevation. On the other side, they sat at a different elevation, and the difference was not gradual or transitional in the way that slow compaction or differential settling would produce. It was abrupt, the kind of abruptness that has only one geological explanation. Something beneath the seafloor had moved. Something had displaced the rock and the sediment above it, and the displacement had been large enough and sudden enough to produce the sharp, vertical discontinuity that was now showing on the monitor in a research vessel anchored in waters that the scientific community had not previously identified as a location of active surface faulting. The lead scientist took a photograph of the screen with her phone. She sent it, with a brief message, to 3 colleagues at universities in Indonesia, Australia, and the Netherlands, who had been working on the regional tectonic picture of the Sulawesi region for years. The message read, "We need to talk about this." The photographs were followed, over the next several weeks, by the full processed sonar data, by the gravity and magnetic data that the vessel had been collecting simultaneously with the sonar survey, and by a series of video calls that grew progressively longer and more detailed as the implications of what the data was showing became clearer. By the time the research team submitted their findings for peer review, 6 months after the discovery in the Makassar Strait, the fracture they had found had been extended in the geological analysis from the initial section of sea, where it was first observed, to a structure that ran for more than 200 kilometers through the subsurface beneath one of the most seismically complex and densely populated island environments in the world, and the implications of what they had found for the communities along the shores of Sulawesi and for the